it's time to welcome the person who has written this proposal with me. Somehow, the Simple Research School was the brainchild of Tim Roemer, and he is the one who wrote the whole script of the Simpa School. So it is a privilege and an honor to introduce Tim Roemer here. And Tim Roemer is going to deliver one lecture, and this is going to be very comprehensive one. Yeah, over to you, Tim.
Yes, thank you very much for the kind introduction. Yeah, here we had this lecture series on polyhedral geometry up to symmetry. And in the first 3 lectures of Ding, this was meant as an introduction to polyhedral geometry, but up to now, no symmetry appeared and no motivation about which questions we would like to consider and stuff like this. So the subtitle is about recent papers of Ding, Thomas Kahle, and myself, which the overall title we call Symmetries and Local Global Principles in Discrete Geometry. So, and as I said, things are done with Thomas and Ding. So, in the very beginning, I would like to give some motivation. In particular, you will see many statements and results which appeared in the first 3 lectures of Ding about, especially about cones and stuff like that. So, in principle, that you should know from the last days. And in particular, I will also say a little bit about what are our motivating questions in this area of research. So what we would like to understand and what is the global picture for it. I mean, the local picture is somehow what you saw so far. So a cone living in some a vector space, finite dimensional vector space is a local object in our wording. But the global point of view is not yet visible, but I will come to that. And in the third part, I will combine the 2 areas, so the classical results, which you saw already in the week and which I repeat in the motivation part, and then what do these classical results mean in this new setting. And please interrupt me if you have any questions at some point. And yeah, Imran, you should say me if there's something in the chat, because I don't see anything at the moment. Good. So our main object is at least locally, is a convex cone in some R space, in a finite dimensional vector space. So you see it and you saw it already. So you take a set of nonlinear, linear equations by non-negative coefficients. So that gives you such a convex cone. And usually, and in our case, it always comes with a generating set. So that is this capital X here. This generating set might be infinite, might be finite. So, but if it's finite, then you call this cone finitely generated. But not all cones are finitely generated, so one should say. But usually, I would like to consider the finite generated situation. And because it also appeared, at least in the way that yesterday some integral polytopes or integral cones played a role, a little bit more general, which is not really the case. We consider rational objects. But rational objects means for a cone, it is the same thing to say that the generating set is, you can choose a generating set which consists only of lattice points. Because once you have a generator, even if it has rational coordinates, you can multiply and replace that generator by an equivalent one up to multiple, which has only integral points. So lattice points, and so that is not really a difference in this setting. And below you see a picture, so that is a typical cone, which we would like to consider. It is finitely generated, so it has here 2 generators. on the race of that cone, so it's rational in the sense of the definition. I also you see all the lattice points in that cone that appeared yesterday, for example, in this Erhard theory. So cones, you can be interested in cones from various points of view. So if you come from algebraic geometry, then you are maybe interested in toric geometry, and then polytope and cones appear naturally by describing the affine pieces of a toric variety. If you come from polyhedral geometry, that is here the point of view, then it's the object by themselves, which are interesting. It has nice, and then that is the connection to Erhard theory. It has also applications in combinatorics. So here, if you consider the lattice points and you slice them around hyperplanes, and you count how many points you see on such an hyperplane, then this is something which has deep relation to the Erhard theory, in the sense that there you would take a cone, a polytope, for example, a lattice polytope, embedded one dimension higher at height 1, take the cone generated by it, and then you see that the k times multiple of that polytope appear really as slices in that cone, and the lattice points you count by that Erhard function are really the lattice points on those slices. So there's a cone version, or an interpretation of these of all these construction from yesterday using such cones. So, but today, for simplicity, I stick to this cone situation, and I will not speak much about polytopes. But many things here have also a polytopal version, or interesting questions on the polytopal side. Good. So what is the motivation? So we saw that there exist several fundamental results about polytopes, cones, and so forth. So, and I will recall 3 of them. So, and they will play some important role in our application. So the first one was the theorem of Karateodori. So the theorem of Karateodori tells you the following. Let's assume you have a cone living in R to the n, and you can take an element of that cone, so that is this small x, and you can even do it a little bit better than just compare it with n, but you can take the dimension of the cone. Maybe the cone is not full dimensional, so the linear hull of the cone might not be the complete space, but maybe it's living in some subspace. So the statement is there exist always m elements in the cone such that your arbitrary chosen elements x is a linear combination of those. I mean, a non-linear using non-negative coefficients, of course, and you only need up to d many of those elements. Of course, for each x you need different x1 to xm. So it's the choice of x1 to xm is dependent on that x, but it means that you cannot have element. So the linear combinations you need, the length, if you call that m the length of such a linear combination, where all coefficients are non-zero, then the length is bounded. And geometrically, that was also explainable, because you see that that you can, so to say, triangulate such a cone. So that was yesterday, I mean, Ding gave as a motivating picture for the polytopal situation. Let's assume you have in R2 a polytope generated by 4 points, but then you see that you can make a cut in the middle, then you can triangulate the polytope in 2 triangles, and every point in that polytope will be a linear combination of 3 elements of one of the triangles, of the vertices of the triangles. And a similar thing is true here in general for polytopes, and even also for this cone situation. So you can triangulate your cone, and this triangle in this triangulation, so that is smaller subset of cones, so such that the union is this cone C, and they satisfy some nice intersection properties if you do it in a good way. And but for the maximal dimensional cones in such a triangulation, you only need up to d many elements generating such things, and that is the geometric point of view of this theorem. Okay. The second result is maybe even more important. So that's a fundamental result of Minkowski-Weil, which says in the cone version, you can express cones in two ways. And that is also how you can geometrically visualize yourself. So the first way is what is here the first statement. So if I have a cone, then which is which is finitely generated, so the x exists x1 up to xm, such that the cone is finitely generated. So you are only considering such cones for that statement. Then there always exists linear forms, lambda 1 up to lambda s, so about the s you don't know, such that the cone is also can be considered as the set of x's which are the solutions of the linear systems of inequalities you get from that linear forms. So from linear algebra, we know very well how systems of linear equations appear in this lambda I. If you choose coordinates, then it's just a linear equality, but not an equality, but an inequality. And one of these lambda i's, if you set lambda I of x to 0, then you get an hyperplane in the space. And greater or equal to 0, that means those x's are living on one half space induced by the hyperplane. So if you have a hyperplane, then you have a left half space and the right half space. And one of those half spaces is induced by that inequality. And finally, many of those inequalities suffices to describe such cones. So in this sense, this cone is a similar object as what you know from linear algebra if you consider solution sets of linear systems of equations. And the picture below here gives you the 2 point of views. Okay, and the statement of Minkowski-Weil is that those things are equivalent. But the picture on the bottom states, okay, either you can consider your cone as an object which is generated by elements. So you pick maybe on each ray, so on each one-dimensional subcone of your cone, you pick an element, and then everything is every element is a linear is an equation in these elements using non-negative coefficients. So that is one point of view. And the other point of view is, that is here the colors should a little bit illustrate that you can cut your cone by hyperplanes, and the cone is then what is inside these intersection of hyperplanes. So you cut your cone in this out of the space using hyperplanes. And Minkowski-Weil, which is a non-trivial result, states that those two things are equivalent. So either your cone is finitely generated as a convex cone in the sense of the definition given a slide before, or it is it can be seen as an intersection of finitely many linear hyperplanes. And okay, if this would be interesting, of course there might exist many ways, but if you choose minimal, so if you choose S minimal, then these hyperplanes are uniquely determined and are called the support hyperplanes. And from the support hyperplanes, you can also see the facets of the cone, but that is something which has not of relevance in this talk, but at least in the picture, you see these, there are two facets, which are these two orange one is a red one is a yellow one at least in my colors, which I see on my screen. And the color in the back here is kind of violet here, but rosé, maybe it's more rosé, but anyhow. Good, that is the second fundamental result. And that is also, I mean, because in the I gave you already 2 slides ago some connection to algebraic combinatorics via Erhard theory. Here's the deepest connection to optimization, because in optimization particular problems in optimizations are studying objects which are defined like here in the second part. So that is really, I mean, the people in optimization wouldn't, I mean, the geometric point of view is then the cone version, but the optimization point of view would be to look at systems of inequalities if you do linear optimization at least.
Professor Roemer?
Yeah.
I have a question. Basically, you have defined the convex cone. Whether if we apply the extra condition such that in the definition of convex cone, summation of all AI becomes 1. Yes, in this definition, if we apply the summation of all AI, where I runs from 1 to m, that result becomes 1. Could we say that this convex cone becomes a convex set?
Depending on your coefficients. So if you just insist on the equation to be 1, but don't say anything else about the coefficients, then you get an affine space. If you say that the coefficients are still non-negative and the sum is 1, then you get a polytope. So I mean, there are different ways to these objects we saw in the last lectures of Ding and here. There's always some kind of intrinsic definition in terms of equations. And for the cone version is given here, but what you say is, I mean, at least if I understood your questions correctly, then you were close. No, you were at the definition of a polytope, of a convex polytope.
Yeah, I got it.
But there's always that is what Minkowski says. There's always another point of view, and here the connection is really to I would say that's the deepest connection to optimization, which makes that Minkowski wide. I mean, it makes the theorem is really powerful and interesting from various points of view, but also from the point of view of optimization. And the third statement I would like to recall is because it is maybe, or that is a deep connection to algebra, especially commutative algebra. So that statement here by themselves is not a commutative algebra statement, but the commutative algebra point of view is based on that statement in an essential way. So if you have a finely generated rational cone and you intersect it with the lattice, here the ambient lattice is z to the n, then this is a finely generated monoid. So that was the question. If you take that monoid, you take the associated monoid algebra, then you, in commutative algebra, things should always be finely generated in some sense. And it is essential that this monoid here is finely generated. And okay, I mean, this last theorem here is just a connection that if you choose the irreducible elements, then you get really a generating system of your monoid, and that's called the Hilbert basis of the monoid. And if you see the picture here, so the monoid is really all lattice points in that cone. So all lattice points you see on that, which are in the yellow area, but also of course on the boundary, and then also 0. So for monoid we need 0. And here it turns out that the of course the lattice points on the rays, so these one-dimensional rays here, always will be, I mean, the first one you see on that ray will always be an element of that Hilbert basis. And you, for a second, one could hope that these are all, but that is not true. So you see, if you make that example here explicit in terms of equations, then you see that you need 2 further lattice points in the interior of the cone to generate all other lattice points as sums of those 4 points. So what I claim here in the picture is that every lattice point is a sum of those 4 points up to multiples, of course. You can add them as many times as you want, those 4 points, but up to that multiples, everything is given by the 4 points, but you need really the 2 points in the interior. So that is a crucial thing to observe, that the number of elements in the Hilbert basis can be significantly different to the number of lattice elements coming from these rays, which are, I mean, those elements on the rays, they suffice to generate the cone, but not the monoid alone. Okay. So that was a recap of the lecture series from so far. And just one side remark is that things are, and it's not so clear why, but things are depend a lot of that our cones, our objects from polyhedral geometry are living in finite dimensional vector spaces. But there exist also other spaces of interest. So for example, here, the one which we are considering many times in our papers is this R infinity. So that is the set of sequences of real numbers, but only finitely many are allowed to be non-zero. So, and these spaces, I mean, it's also a fine, nice R vector space. It's not finite dimensional anymore. So, but these spaces appear, if you look at, I mean, there are now various points of view how to look at them. For example, maybe in optimization, you have an increasing number of systems of inequality in larger and larger spaces. Or in geometry, you are looking at cones coming in families, which are living in larger and larger spaces. So, I don't know, for example, you take the cones generated by the, I mean, if you take the probability matrices, which have, so n by n matrices, which have with the rule that there's only one in one row and one column and zero else, and they generate a nice cone which appears in probability or has some importance in probability theory. But now you let n vary, then you get larger and larger cones of those ones. So you can look for limit behaviors, and this limit behavior becomes visible in these larger space. For example, in this large space R infinity. So here's the motivating question for us. So very simple in this sense. So now take a cone defined in a similar way as in the finite dimensional situation. What can we say about this cone? So what are analog results about classical results, especially those ones mentioned before, or other things of interest? So what are the applications for the finite dimensional setting? Okay, I mean, one can ask many questions, but that does not mean that one gets any answers. So in general, one will not see too many things because this question is too vague and too general. And okay, but you can at least cook up examples. So for example, in R affinity, you can look at all standard basis vector, E1 up to EK up to and so on. And then you take a cone generated by it. It's a nice cone. So it's the analog of the orphaned of non-negative elements in R to the n, but now sitting in R to the infinity. Yeah, it's for sure it's not finally generated, for example, because you cannot get rid of any of these basis vectors EK. So everybody of those ones is needed. So if you take one of those away, then it will always be a smaller cone which you get. So that is, for example, one thing you see. But in some sense, and that is the starting point of our study, this example is not so bad as it looks like. So well, here very explicitly one can say in some sense it's finally generated, and what you should observe, and there the symmetry point of view comes into play, which hasn't had any up to now in Ding's talk. You never saw symmetries appearing. So what we need, or for this example, we need a special group action. So on Rn, you can induce a group action of the group of permutations of n elements, which are called here sim n, just by switching coordinates. So you say, if I have a permutation sigma and I apply it to a standard basis vector ek, I map it to E sigma of k, and linear combinations are mapped to the induced linear combinations. So the only thing which we are doing here is we are change. I mean, the coordinates x's are permuted, and then of course you can look at the union of those sim n's. I mean, of course, one should be a little bit careful. So sim n sits in sim n plus 1 as a stabilizer of n plus 1. So it makes sense to consider this as a union. And then you see that on R infinity, so the space which I gave you a slide ago, or defined a slide ago, you get the induced action, which is really the same definition. So there's no difference. But then some miracle happens or appears. This cone, which we saw the slide before, is just generated by one element up to symmetry. So if I take E1, the first basis vector, and I take the complete orbit of E1, but then I get all EKs, because I always find a permutation mapping E1 to any arbitrary EK. So in the orbit of E1, every EK is sitting, so it's a cone of one orbit. It is not finally generated as a cone in the strict definition, but it is finally generated in this new way. It is finally generated up to symmetry. And here a very essential point appears, and that will appear many more times in this talk and in our papers and other papers. So somehow there are now two sets of information. So the one set of information is a finite set, and here it is being finally generated up to symmetry by one element. So this is here in this example E1. And the second set of information is coming from the combinatorics of the group action. So there are two pieces what you need. I mean, before before considering this symmetry, we had no combinatorics coming from symmetries. Here we have some finite piece of information, and some the infinite piece is existing, but it comes from a natural, if you call this group action natural, at least it comes from a natural explanation. And I say combinatorial explanation because for me the sim n and the group action defined in that very particular way is some very combinatorial object to consider.
Tim, just curious about what do you mean by applying the symmetric operator? Are there cases that we would not obtain a cone?
No. So sim E1 and the orbit. I mean, if you take an arbitrary permutation of n letters, then E1 is mapped to some element EK. So I mean, this is a notation for the orbit, which means it's all elements which you get by applying some sigma to E1. So you get really the set E1 up to E2, E3, up to EK, and so forth. So it's a set. It has no additional structure except that it's a set.
Okay.
Of course, you might ask if you are very careful and you say, why do we consider this artificial looking sim infinity and not the complete symmetry group of the natural numbers, which is much more natural, in some sense, much more natural to do. It's a much huger group. So the difference is that sim infinity only consists of permutation which permute finally many elements, where the symmetric group of the natural numbers consists of all permutations of the natural numbers. But they might also exist also permutations which move every element around. But on the level of orbits, this doesn't make a role. And here it plays a role. It's important that our elements are living in this R infinity, so there are only finitely many elements, coefficients of U's which are non-zero. And then you can prove a small exercise seeing that the orbits are not changing. But from the technical point of view, if you prove something, it's much easier to do it with this sim infinity, which are called here even only sim, instead of this complete group, because sim n, because this sim n is just too huge. Anyhow, now we can consider cones, and we are not considering all cones, but only those which are sim-invariant, in the sense that if you take an arbitrary element of U of C, your cone C, and an arbitrary element sigma of our sim group, and you then you ask for that the element sigma applied to U is also an element of your cone. So the example was here. The example on this slide was of that kind. It's a symmetric cone in this sense. And we see that it makes no sense to ask questions about cones up to symmetry, so cones up to these group actions. So here's the general, our general strategy to study something. So we would like to study sim-invariant cones or polyhedral objects more generally on R to the infinity. And they are relations, so it's not that it comes from, I mean, we were the first ones who considered such object. So at least ideas and methods were heavily motivated by results from commutative algebra, algebraic topology, representation theory, and here's some authors related to those approaches: Church, Dreismer, Ellenberg, Hiller, Sam, Snowden, Sullivan. So there are nice connections to algebra, and somehow we took the ideas and wanted to understand the corresponding implications in the setting of discrete geometry. But you don't have to understand the algebraic background to study this setting here in discrete geometry. But there's also one significant difference for those ones who know these notions here and maybe had a look at those papers. There are, in many cases, this Noetherianity property played an essential role, or at least being Noetherian up to symmetry, whatever this means. And here in our setting, we are far away from this kind of, we don't have an ambient object which satisfies some Noetherianity assumption. I mean, a polynomial ring in finely many variables satisfies Hilbert basis theorem, so it's a Noetherian ring. But our ambient spaces are too ugly for that. So that causes a lot of difficulties for us. So now I have said a little bit about the motivation, a little bit about the where symmetry enters the picture. And now we come to or I would like to discuss our 2 points of views. So we have a local view on these objects, and I will come to that, and a global view. And the global one, that is the one I talked to, I spoke about. So a cone in R infinity is a global object. So it's one object sitting in a global space. To such an object, you can associate local objects, which is a chain of cones actually. And so what you would like to have is cone Cn in R to the n. And you ask for the question whether the global cone C is the limit of those cones, so it's a union of those Cn's. So the union of all R to the n gives you exactly R to the infinity. And then you would like to have that the union of those cones is C. But you would like to have it a little bit more. It should be compatible. So what you would like to have, okay, one thing you would like to have is that it's an increasing chain in this very, that Cm is contained in Cn if m is less or equal to n. So it should not be artificial. And each Cn is sim n invariant in its ambient space, R to the power n. Of course, you might ask, does such things exist at all? And but it does. So if you take the global cone and you just intersect it with R to the n, you get a cone Cn. And then you can prove that your global cone is really the union of those cones which you get in this particular way. And those cones will satisfy here 1 and 2 if this global cone C was a sim-invariant cone. But be aware of the fact there exist many, many ways to associate such chains such that these properties are satisfied. This is simply by the fact, even if you give me such a chain, you are allowed to delete, for example, as many cones from the beginning and replace them by 0. This will not change the union. This will not change these two properties. but you get a different chain. So there exist many chains having, satisfying here 1 and 2, and such a given fixed global cone C is the union of the elements of this chain. Okay, but that is the local point of view. And vice versa. I mean, if you have such a chain, actually, you can, of course, just consider the union. Then this union will be a sim-invariant cone in this in the way I defined it before. And yeah, so you can always consider the global point of view, the local point of view. The global point of view induces a local one induces a global one. And yeah, it's a question whether you like to consider one object sitting in a very, very, very large space, or whether you would like to consider the cones as an increasing chain of cones. For example, if I come to that application or this connection to optimization, then the connection would be you're really looking at systems, solution sets of systems of inequalities, and then you apply the systems are now considered in larger and larger spaces, and then you're looking at these cones you get there, and then you see it from this point of view. So that depends on your personal application, personal chosen application, which point of view is more important for you. And for certain questions, the global point of view helps you. For other questions, the local point helps you.
Tim, regarding to this global chain, the dimension remain the same, right?
The global one here, the
CN
makes this CN can, yeah, this can have maximal dimension n, but you depends on what C is. I mean, if the global C is just a zero cone, then the local C's will be the zero cone, so it will be very small dimensional. I mean, dimensions will be very small.
Dimension is not increasing in any step. So just applying the
not necessarily, not necessarily. So it depends on the cone C what happens. So the question, I mean, your question, what happens to dimensions as a sequence, as a function in n, heavily depends on that cone C, of course, here.
Okay.
Okay, but this call, I mean, just to to give you some definitions globally and locally. I mean, the global definition are already used. A cone, a sim-invariant cone in R to the infinity is called sim-equivalently finitely generated. So finitely generated up to symmetry. If there is a finite set X such that the cone is not finitely generated as a cone, but it's generated as a cone by finitely many orbits. So this sim applied to that X, since X is finite, it is a union of finitely many orbits of the element of capital X. So that is the essential, what is inside this definition. And of course, now you might ask yourself, so what is the local point of view of that definition? And that looks at first a little bit artificial, but once you see it carefully, you see that it is really the right one to consider. So at first one, there is this, the notion of stability. So such a stain stabilizes if the cone Cn finally, for n large enough, can be explained totally by previous cones. So if m is less or equal to n and you need a starting point r, so here for all n greater or equal to m, greater or equal to the 1r, you would like to have that Cm is a cone of the orbits of Cm. So here you see it again, the 2 point of view. So there's, I mean, if you now take m to be r, so then there's a geometric piece of information, then comes a combinatoric piece of information from that group action, and of course you have a cone closure to consider, but that gives you everything you would like to know about Cn. So there's a systematic way to get Cn if it stabilizes. And the support size just plays a role in the next one of the next statements. Just if you have an element in R to the infinity, the elements which are the number of elements non-zero coefficients is the support size of a vector. And here is a very good example of a local global principle. So if you have a cone C of a particular type, I mean, it's not an arbitrary result, so you have it is a union of cones in such a sim-invariant chain with some additional assumptions. So Cn should live in the non-negative part of Rn. But C is the union of those Cn's. And then the following statements are equivalent. So C, the global object, is a sim-equivalently finitely generated cone. So it's finitely generated up to symmetry if and only if this chain here stabilizes in the sense as given above, and each cone in the chain is not all cones are finitely generated, but they are finitely generated from a certain point on. So that is my notation if n is large enough. In these kind of statements you would like to see. So any kind of interesting property, either locally or globally, you would like to translate between the 2 point of views. And there's a third statement which explains two a little bit more explicitly, or now there's even a further point of view. I said a little bit about the saturated chain. So finally, if this theorem holds, so if the three statements are true, finally the chain has to be the one induced by the saturated chain. In the beginning, some ugly things can happen, but finally the saturation property is satisfied. And you can even say something about it's not only finitely generated, the Cn finally, but it's also generated by elements of support size at most S. If S is the natural number from the point on, these two statements are true.
Tim, does there exist a chain which stabilizes for small value of n?
Yeah, sure. I mean, okay, the most trivial example is again, takes a chain of 0 cones.
0 point, yeah.
But
for one
more,
some non-trivial one.
Yeah, but take I don't know, take any cone in let's say R2, and then you can take the induced chain. If you take this as a definition here, this line as a definition of all other cones in that chain, then it will be generated, will be stabilized from step 2 on.
Ah, okay.
I mean, you can construct always chains stabilizing from any point you want. If you are the one who's constructing the chain, you have influence on that point. But for a general chain, that is an open question. I don't have any clue. A good estimate. So what is this S here? So or from which point? So what is the stability index in general? So I give you just a chain of cones. I give you some data, some combinatorial data of that chain maybe, and you should give me an upper bound for the stability index. I don't know, even not for specific families.
This holds for infinitely generated cones too?
What?
This kind of construction. That's so the cone which is being determined by infinitely many generators. I
mean, no, we here not finitely many generators. So up to symmetry, they are finitely many generators. So I don't get your question very well at that point. So, but maybe we can talk about that later, because there's a general philosophy, which is a side philosophy of that of our study, and that can be explained by what can go wrong goes wrong. So whatever I'm talking about, whatever could go wrong goes wrong. That is our experience. So I mean, here's one example of that. What does this statement mean? So you could hope for that all cones are finitely generated, for example, or that all cones are in the chain. I mean, if that theorem here is true, you could hope that all cones are finitely generated or all cones are saturated. But what can go wrong goes wrong. So here's an example. So you take C2 as a cone of all elements in R2 such that the coordinates are greater than 0, and you add 0, 0. And then you take Cn as the non-negative part of Rn. And then you see immediately that this chain here, it's a sim-invariant chain in the definition. It stabilizes from n greater or equal to 3 on. I mean, the Cn's here are finitely generated from n greater or equal to 3 on, but not C2. C2 is not finitely generated.
Yeah,
This
I
is
was talking about exactly the same.
okay.
Same example. My question was about the same example.
And then you take the cone, the union of those cones, and then you see we get a very nice cone back, which is the one which we saw on all the examples so far. It is really the cone which is generated up to symmetry by E1. So it's finely generated up to symmetry, but not all cones are finely generated. So C2 is not. Not all cones are saturated because C2 is not. So it's essential to see here this. There is an S, and this S is non-trivial, or the S also appears here in the second statement. So there's no hope that you get it done. I mean, that is also a way of explaining this. If you're considering such chains, the beginning of such a chain can always be ugly. It finally becomes nice. So that's a general point of view. So since time is running up a little bit, is running a little bit, I will say a little bit more. I mean, okay, I gave as motivation 3 fundamental results of, or basic fundamental results, depends on the point of view of discrete geometry. We also have a version for Kara-Theodori. So if C is a sim-invariant cone that is equivariantly finely generated, and the set consists only of the coefficients of the vectors in the set are all non-negative, then any element in your cone, global object, can be written as a conical combination of S elements. Yeah, as many elements if S is the cardinality of the support size of your view. So that is the global analog. Of course, here's another example of what can go wrong goes wrong. So here, for example, you could hope to get rid of the assumption that the X is considered, the generating set X of your cone is considered in the very particular way. So it has non-negative coefficients, the elements in this generating set, but then you immediately see, take that cone generated by 1, 1, 1 minus 1, the orbits of that and the cone generated by the orbits. And then you see that, by definition, every element in the generating set has support size 2. I mean, here 1, 1 has support size 2, considered as an element in R infinity, and 1 minus 1 also, and also all induced elements in this orbit here. But for example, E1 is a linear conical combination of U1 and U2, has support size 1. But it cannot be a conical combination of one element of the generator, because if you have only one element of the generating set, it has support size 2. It will always have support size 2, whatever you do, by multiplying it with something, some positive number. Anyhow, so as I said, what can go wrong goes wrong. There's also an equivariant Minkowski-Wild theorem. I skip maybe the local version because that is a little bit technical, but essentially it says that finally the situation stabilizes in the sense that if you consider the correct way of duality in the dual cones. But I would say for the local version here, if you stick to the, if you're interested, you can have a look at our paper. What is still missing is a global, that is interesting. A global version of Minkowski is somehow a little bit easier, more difficult to get. It's not even not clear what is the one. So what you really would like to say is something like that. You would like to have consider a cone, and then you can define a dual cone in a natural way. And you see also that C star, this dual cone, is sim-invariant, but you would like to have a statement like that this is finely generated if C is so. So finely generated up to symmetry, of course. But then we stated this cannot be. So usually it will not be. The dual cone is never finely generated in this sense. So the most prominent version of a global equivariant Minkowski theorem can simply be not true. And somehow the local version, how complicated it looks like, is a good replacement locally, but the global point of view is still mystery what should be the correct statement here. Maybe we have to consider other dual objects, but we have doubt about that. maybe you have to add a little bit more information here. We will see. But satisfactory, I mean, very nicely, a global equivariant Gordon lemma exists. So if you have a semi-equivalently finely generated rational cone, again with some additional assumptions, so it's living in the non-negative part of R infinity, and you take the monolith generated by it, so intersect it with the lattice C to the power infinity, then this monolith is sim-equivalently finely generated, is a sim-equivalently finely generated monolith if you define it in the appropriate way. Again, what goes wrong can go wrong. So rationality plays a role. Maybe I forgot to state it as part of the assumption, but the cone has to be rational. Everything here in these assumptions are necessary. So in summary, I would say that so the semivariant chain of cones, monolith, polytopes, whatever you would like to consider in polyhedral geometry or algebra, are rather complicated objects, but also very interesting to study. And what we did so far is to start to develop a theory for saying something about these objects, but still many things are left. And of course, also applications would be nice. I mean, for example, what is the corresponding Erhard theory, or something like that. So, and we see our work as first steps into a development, what one could call discrete geometry up to symmetry. Thank you very much.
Thank you, Tim. Thank you very much. Let's applaud for Tim. Okay, there are a few questions in the chat box. What is the intersection of any 2 or 3 chains?
Well, 1 second, let me just let me just come back. Yeah, now I see you. So sorry, what was the question?
I think IBA Karachi, can you state it yourself? It is not complete. What is the intersection of any 2 or 3 chains? They were not talking about the chains. What kind of chain you are talking about? Probably, Tim, they are talking about if one construct 2 different chains,
yeah,
sim-invariant chain. So what would be the intersection of the chain at different level, whether it would be a sim-invariant chain as well or not? Probably this is the question. Probably, I try to translate it.
Yeah, you mean whether depending if now, I mean, at first you could try to consider, of course, natural constructions which are interesting from your point of view. If you want to intersect objects, but you must be careful. As I said, so what goes wrong goes wrong. So in this sense, I mean, of course, in your case, you would like to, maybe, I mean, I can only guess what is meant. So maybe you would like to consider 2 chains and intersect in each Rn the corresponding cones or something like that. And then you would like to consider the resulting chain, which is of course a chain. And then you might ask yourself, can you say anything about the properties of such a chain? So in general, it's a nice or it's an interesting construction. We haven't looked at that at the moment, so I cannot say too much about properties like what is satisfied or not, or how things, if something is satisfied like stability, how these are related. But of course, one could study such questions.
Yeah, thank you. Are there other questions? Yeah, please go ahead.
Professor Tim, actually this lecture is some kind of interesting to me that I from analysis, I have no very strong background in algebra, but we are working in mathematical inequalities and they all are defined in convex sets. I'm willing to connect this idea, the idea of convex cone with the convex set. So my question is that whether we could generate those inequalities which are defined in convex sets like Jensen inequality, Jensen-Mercer inequality, could we apply this idea of convex cone in those type of inequalities? Oh,
So I don't know whether I got the question correctly. So what is, I mean, what for sure goal is possible. I mean, I talked now about cones because in our last paper, we had in particular in mind to prove these three fundamental results of discrete geometry. But of course, this framework I mean, you can study chains of convex sets, for example, and you can look for symmetries on such chains. So in general, there's a categorical point of view. So in this sense, you would, I mean, there's a notion of an Fi module, which corresponds to such a chain, and you evaluate that Fi module on objects. So here in that talk, the objects were cones. But you could also do it with convex sets or groups or whatever is your object of interest. So here we did it in our papers now for cones, polytopes and stuff like that. And then, of course, a natural thing is what you see locally, maybe from your experience, from classical results, some inequalities or so. Then you might ask, so what is the global point of view? What is the limit behavior? So that is the general philosophy. And our three statements here were a particular example where one could prove something in a nice way.
Could you please take some references or books regarding this topic?
So Imran, unfortunately, I have to leave now.
Okay, Professor Tim has to go for a quick meeting. Regarding to the references, I will share. Okay, it is very easy. Just Google Tim Roemer and see his paper on archive. So
but
probably his one paper. His one paper on FIODO.
If anybody has question, you are welcome to contact me. I will come back to this closing ceremony.
Okay. Bye. Thank you. Bye-bye, Tim. Bye-bye. Regarding to IBA Karachi, we can continue the discussion a little bit on this particular topic. This is a kind of a topic which was introduced not in algebra. It came from category theory from the paper of Thomas Church and Farb. And that topic was extensively explained in that particular paper of Thomas Church and Farb. And it has been of interest for the persons working in the area of algebraic topology for a longer time. I think the year when the paper appeared was 2004 or 2005. Later on, many areas like algebraic statistics, people from different disciplines, they picked that because anything which appeared in the category theory that is of interest of different areas of math. So they picked this particular sequential idea and applied it on various concepts. And I don't, probably me is not familiar with the analysis side, but regarding to your question, there would be an interest because I do understand in analysis paper are interested on a particular setup where they consider some specific type of convex set where a certain inequality satisfied or holds. So one can extend this particular idea for looking at, okay, what about applying the sim operator or there are other operators too, similar kind of, and extending that inequality concept in the sense of sequentially. So you go to, okay, you find some convex set in R3 and holding some particular inequality, you can extend it to R4, R5, and then so on. So this would be an interesting area for analysis people. In algebra, things started with the paper of Tim Roemer and Uwe Nagel. I think that appeared in the year 2010 or 11. And since then, there is a lot of interest in this particular direction. And he already mentioned a lot of things in his talk. So yeah, this area is widely open. And I think anyone can build from any particular topic and looking at the sequential properties under the same invariant operators.
Can I add one comment?
Yeah. Please go ahead.
So I mean, actually, in our paper with in paper of Thomas Kahler, Tim, and myself, actually we developed a rather general statement for chain of set not only for cone or monolith. So we start by studying chain of set and a chain of set, and on the chain of set we have some kind of closure operation. So yeah, so a closure operation is an operation that satisfy some axiom, and I haven't checked, but I think the convex operation could be a closure operation. So now, I mean, you have to check three axiom in the definition of a closure operation. So it's say that the closure of a set contains a set if A contained in B, then closure of A contained in B, and closure of the closure is a closure. So the convex closure is for sure a closure operation. So then, I mean, you can certainly consider chain of convex set by using our general reason on chain of set. So yeah, I mean, if you are interested, then I guess our paper have some general reason on such kind of chain. Open the website.
Did you? Thank you, Dean. Thank you very much for your comments. And I think this is always, it always happens when people from various interests are sitting and discussing ideas. So definitely everyone will pick some bounties which is related to their own area. So that's really yeah, that is the purpose of these kind of meetings and discussion, particularly the SIMPA school is one of this kind. Now I would like to share a news with you that there is a summer school on combinatorial commutative algebra on the similar kind of topic, and this is scheduled in August 8 to 12, and this is going to be in the Sabancı University, Turkey, and there are important dates. Okay, for the participants who are interested in this similar kind of topics, so they can register themselves. The last date of registration is 1st June. And okay, for the students and the young researchers, there will be some financial support available. And there is a website, the link is shared in the chat box. Can you go a little bit down, scroll down? Yeah, organizing committee, you can see Narsa Larry is there. And among the speaker, you can see the name, Professor Hibi Herzog, and Sarah Madani, who is also a speaker here. She is also going there too. So this conference is physical, I propose. And by that time, I hope if the COVID situation will remain in control, so this is going to be a physical gathering. This is in August, I believe. And there is another similar kind of activity which is coming in the month of July. It is in the University of Osnabrück. Unfortunately, I could not send you the link. I will share the link in the closing ceremony in the chat box. And that conference is named as 65 plus 70. Dan, can you please confirm what is the name? Can you share the link in the chat box? Dan, are you there? Sarah or Dan?
Okay, so I will search for it. I don't have it here now, so okay.
Yeah,
maybe, or maybe you ask him in the closing ceremony.
Okay, closing ceremony. We will show you that link. Yeah, and that is a conference which is in the honor of Professor Herzog and Professor Bruns, who is in University of Osnabrück. Yeah, Mina, thank you very much. Can you open the link, Numan? Open the link in the chat box. Share. Yeah, we are just opening the other link. So this is the publicity time, anyways, advertisement time. So 75 plus 80, I was wrong, 55, okay. 155 years of commutative algebra. Anyways, this is named after, this is birthdays of Professor Herzog and Professor Bruns. Bruns is younger, and Herzog is turning to 80 now. And this is a school which is going to take place in Osnabrück, where Tim Roemer is there, Dan is there. And let me just tell you that this is going to be the most important gathering of this area of commutative algebra, where you can see the name of Jan Derisma, Alessandro Di Stefani, Martina Kovetske. She's already in University of Osnabrück. Then Thomas Kahl. So these are the confirmed speakers, and definitely Herzog and Bruns will be there. Tim Roemer will be there, and many important persons in the area of commutative algebra, they are going to be there. So scroll down a little bit. So you can see the list of keynote speaker, Aldo Conca, Hibi, and almost all the famous names are there. So don't miss this opportunity, particularly the young, all kind of researcher. This is a good opportunity to grab. Okay, these are few advertisements. Now we will return. Now it's break for the lunch, and we will resume again at 3 o'clock with the closing ceremony. Please stay tuned. Thank you. Thank you, everyone.